Welcome to the deep dive. Today, we're looking at something pretty incredible, the European Space Agency's Gaia mission.
Yeah, a really ambitious project.
We got this fascinating early report from a listener detailing how Gaia was designed to handle just, well, an absolutely staggering amount of astronomical data.
Hmm.
So our mission today is to unpack the really clever technical thinking that makes it all possible.
That's right. And this report, it goes back to the early days, around 2000, the initial feasibility study.
Right.
And it really lays out the core problems they faced. Basically, Gaia needed to map billions of stars, billions, with crazy precision.
To build this like definitive 3D map of the Milky Way.
Exactly. But the sheer amount of raw data,
Yeah.
just mind-boggling.
Yeah, you can imagine, like trying to photograph every single grain of sand on a beach simultaneously.
And the report makes it clear, sending all that raw data back from L2, this Lagrange point way out in space,
Uh-huh.
it was basically impossible. The data rates just weren't there.
Right, not feasible. And plus, constantly reading out the whole detector, wouldn't that add a ton of noise?
Exactly. It would drown out the faint signals,
Yeah.
especially from distant stars.
Okay, so the big problem. Too much data, too much noise, not enough bandwidth.
Precisely. So the central question was, how do you sift through all that cosmic light, find the good stuff, the valuable info, without getting totally overwhelmed?
And the answer?
The report shows Gaia's brilliant solution is this really sophisticated onboard system. Detection and data processing happen right there on the spacecraft.
Ah, so it's smart. It decides what's important before sending it home.
You got it. It prioritizes.
Okay, let's dig into this. This report you mentioned, ESA-SCI 2004, 380 pages. That's hefty.
It really laid the groundwork. No quick calculations here.
A deep investigation.
Totally. And one key thing that came out was identifying, get this, 15 crucial preparatory technologies.
15, wow.
Yeah, 15. It really shows Gaia wasn't just about tweaking existing tech. It needed, like, fundamental breakthroughs.
Reinventing things, like detectors, data handling.
Exactly. The report goes into specifics. Advanced CCD performance, for instance.
Those are the sensor chips, right? Like digital film.
Right. They needed these special CCDs that were three-side buttable.
Meaning?
Think of tiling a floor. These chips could be placed together really closely on three sides, almost seamlessly.
Ah, so you could build a much bigger continuous sensor surface.
Yep. Essential for Gaia's giant focal plane. Tiny pixels, super high performance. These chips weren't off-the-shelf items.
Okay, so amazing CCDs. What else was on that list of 15?
Well, you needed the large focal plane assembly itself, basically, sticking all those CCDs together reliably.
A giant mosaic.
Then high-speed, low-noise detection chains, that's the electronics, to actually read the data off the chips without messing it up.
Without adding more noise.
Crucial. And then efficient onboard data compression algorithms.
Because even after you pick the important bits, you still need to squeeze them down for the trip home.
Right. The telemetry pipeline was still limited.
It's quite a chain of challenges.
And it keeps going. Optimized electronics to manage all that processing on board. A non-moving phased array antenna.
Non-moving. How does that work for sending data from deep space?
It steers the beam electronically, not mechanically. Much more stable and reliable for that high data rate needed from L2. Less complexity, fewer things to break.
Clever. Okay, what else? Physical stuff.
Big time. Large silicon carbide mirrors for the telescopes, very light, very stable, and ultra-stable structure to hold everything perfectly still.
Precision is key.
Absolutely.
Yeah.
And a huge 10-meter deployable sun shield. Part solar array, part umbrella.
To keep things cool and powered.
Exactly. Temperature stability is critical for the instruments.
It sounds like building a watchmaker's masterpiece, but on a massive scale, in space.
That's a good way to put it. And the fine control needed. Micronewton thrusters.
Tiny, tiny pushes for attitude control, keeping it pointed just right.
Incredibly precise. And even things like inchworm actuators for refocusing the telescope.
Inchworm, like tiny little robotic worms.
Sort of. Making minuscule adjustments to the focus. But those tiny changes have huge impacts on data quality.
So even before you get to what data to keep, just building and operating this thing was a massive technological hurdle.
Absolutely. But let's pivot to one of the core innovations that handles the data flow itself. Time-delayed integration, TDI.
Okay, TDI, this isn't like a regular camera, right? Usually you open the shutter, collect light, close it, read the chip.
Right, standard CCD imaging.
Yeah.
But Gaia is constantly spinning, scanning the sky. It doesn't stop to point and shoot.
So how does TDI work with that constant motion?
It uses the motion. Imagine the star's image drifting across the CCD chip. As it moves, the charge collected in the pixels literally gets shifted electronically along the detector columns, perfectly in sync with the spacecraft's rotation speed.
Whoa. So the signal, the exposure build up as the star moves across the chip, no stopping.
Exactly. It's a continuous scan and integration process, like painting smoothly without lifting the brush.
Okay, that's clever. But it sounds like it really depends on those advanced CCDs you mentioned earlier.
Absolutely critical. Their performance is key. How fast can you shift that charge? That's readout rate. How much noise does that shifting add? Readout noise.
Right.
How much charge can each pixel hold? Full wall capacity. What happens if it overflows? Charge overflow
And
handling,
you're in space, so.
radiation damage,
Yeah.
and charge trapping effects over time. All of that had to be factored in and minimized. If the CCDs weren't good enough, TDI just wouldn't work effectively.
Okay, so TDI is this elegant solution tied directly to the detector tech. Now let's go back to that data bottleneck. We said transmitting everything was impossible.
Yeah, the report hammers this home.
Yeah.
Gaia is generating gigabits per second of raw data,
Gigabits.
but the sustainable connection back from L2, only a few megabits per second.
Megabits. That's a difference of what, a factor of 1,000?
Roughly, yeah.
Oh,
It's like, as the report implies, trying to drain an Olympic swimming pool through a drinking straw.
Okay, good analogy. And even if you could transmit it all, reading out the whole sensor constantly adds too much noise.
Exactly. That readout noise would just swamp the faint signals.
So full readout is inefficient and noisy.
Right. And what's interesting is the analysis they did, they showed that even if you look down to really faint stars, magnitude 20,
Which is very faint.
very faint, most of the sky, especially away from the Milky Way's plane, is actually empty space. The fraction covered by stars is tiny.
So reading out all those empty pixels is just a waste.
A huge waste of bandwidth, and it degrades the quality because of the noise.
Okay, so the obvious solution seems to be don't send the empty bits, just send small patches, little windows around the stars you actually detect.
Precisely. The report highlights this. Downlink small patches centered on detected objects. That solves the data rate problem.
Drastically cuts it down.
And it reduces the overall impact of readout noise because you're reading fewer pixels. Better signal to noise, especially for faint things.
Okay, makes sense.
Yeah.
But wait, how do you know where the stars are to select those patches if you're not reading the whole thing out initially?
That's the million-dollar question. And it leads right to the next point. Why not just use a pre-existing star catalog? Tell Gaia where to look beforehand.
Yeah, seems logical. We have catalogs, right? Load one up.
They definitely thought about it, but the report explains why that wouldn't work for Gaia's science goals.
Oh, why not?
Well, first, no existing catalog back then really met Gaia's specific needs. It needed sensitivity way into the red part of the spectrum and super sharp resolution sub-arc second.
Okay, so the existing maps weren't good enough.
And even if you tried to make a new catalog just for Gaia beforehand, it wouldn't be as good as what Gaia itself could do. You'd be biasing your results based on the limitations of that preparatory survey.
Right, you'd only find the things the first survey could see, not necessarily what Gaia could see.
Exactly. And maybe even more importantly, catalogs are static snapshots.
Things change in space.
They do. A preloaded catalog would completely miss transient events. Variable stars brightening or dimming, asteroids, comets moving through, supernovae exploding.
You'd lose a huge amount of science. Discovery is waiting to happen.
A massive scientific loss. Imagine missing a nearby supernova because it wasn't on your list.
Okay, so relying on an old map is out, and you need to catch things as they happen.
Plus, for the core science Gaia does, understanding exactly how objects were selected is crucial. The report talks about needing a well-defined selection function.
Meaning?
Knowing precisely your chances of detecting a star of a certain brightness, for example. Catalog completeness versus magnitude. If you use someone else's catalog, your selection function is messy, defined by their limits.
I see. You need control over how you build your sample for it to be scientifically robust.
Exactly. An unbiased survey,
Yeah.
as much as possible. Which leads us to the actual solution they adopted.
The onboard detection?
Yes. Gaia finds its own targets in real time. It uses dedicated sky mapper detectors right at the start of the focal plane.
So it maps as it goes.
And the huge advantage, stressed in the report, is that this detection happens using the same instrument, same telescope, same wavelength range, same angular resolution as the main science measurements that follow.
So it's internally consistent. The detection process matches the measurement process.
Perfectly consistent.
Yeah.
Which gives you that clean, well-understood selection function.
That makes a lot of sense. And this wasn't just one person's idea, right? The report mentions collaboration.
Oh yeah, big time. Over 100 technical notes from the science side. People like Eric Hug were heavily involved. And intense work with the main industrial contractor EADS Astrium, now Airbus.
So scientists and engineers working hand in glove to figure this out.
Definitely. And it's worth noting, they didn't totally throw out old catalogs. They were still useful for initial things, like getting the spacecraft pointed roughly right at the beginning and helping confirm if a detected object was already known.
Okay, but the primary detection is all Gaia. Now, achieving this level of precision, measuring star positions so accurately, that requires insane attention to detail, I imagine.
Oh, absolutely. The report mentions two incredibly detailed accuracy assessment budgets.
Budgets, like financial budgets.
No, like error budgets. One from the scientific perspective, overseen by Jos de Bruyne, and one from the industrial engineering side, managed by Friedrich Safa.
And what did these budgets do?
They meticulously listed and quantified every single known effect, scientific or engineering, that could possibly degrade the final accuracy of the star position measurements. Tiny vibrations, thermal changes, optical distortions, detector effects, everything.
Wow. Talk about rigorous planning, accounting for every little wobble.
It had to be done to ensure they could meet the mission's goals.
Okay, so we have this incredible system. Let's visualize the hardware. What does Gaia actually look like up there?
Right, so Gaia has two separate telescopes.
Two.
Yep, looking at slightly different directions in the sky. They're separated by a very precise angle, 106.5 degrees.
That specific angle must be important.
Absolutely critical. It's fundamental to how Gaia measures parallax, the tiny apparent shift in a star's position as Earth orbits the sun, which gives us the distance. Having two views simultaneously is key, like having two eyes for depth perception, but across the galaxy.
Okay, two telescopes. Feeding into what?
They both feed light onto one single large shared focal plane. That's where all the CCD detectors live.
The giant mosaic we talked about.
Exactly. And the whole spacecraft is slowly rotating, once every 6 hours.
Spinning like a top.
A very slow, very precise top. It spins around an axis that's perpendicular to the direction the two telescopes are looking. This steady rotation sweeps the telescope's views across the sky.
That's the scanning motion.
That's the scanning motion. And this focal plane is huge, as you said. The report mentions 106 individual CCDs.
106. Wow. Arranged how?
And 7 rows across the focal plane. Each CCD has its own control electronics. It's a complex piece of kit.
I'll bet. And as Gaia spins, a star's image drifts across this focal plane.
Right. It takes just over a minute for a star image to travel across the full width of the focal plane in the direction of the scan.
And all this time, that TDI process is happening, shifting the charge.
Continuously. The scan rate is perfectly matched to the charge shifting speed on the CCDs. Each row of pixels gets shifted in less than 1,000th of a second.
Incredible timing. So, where do the sky mappers fit in this layout, the detectors doing the initial finding?
They're right at the beginning, the first 2 vertical strips of CCDs that the light hits as it enters the focal plane.
Okay.
The report shows them labeled SM1 and SM2 in the diagrams, SkyMapper 1 and SkyMapper 2.
And they need to keep the light from the two telescopes separate at this stage.
Yes, there are optical baffles, internal walls basically, that ensure SM1 only sees light from telescope 1 and SM2 only sees light from telescope 2.
Got it. And this is where, as you said, they have to read out everything initially because they don't know what's there yet.
Correct. The report explicitly states that for the sky mappers, all pixels are read out.
At the cost of higher readout noise.
Exactly. A necessary trade-off to make sure you don't miss anything interesting right at the start.
So SM1 and SM2 read out everything. What happens to that data stream immediately?
It gets processed incredibly fast, right there on board. Algorithms look for patterns of light that look like point sources, stars.
Not just random noise or cosmic ray hits?
Right, they filter out cosmic rays hitting the detector, they identify the star candidates, measure their brightness and initial position, and even use this data to very precisely measure the actual scan rate of the spacecraft at that moment.
Wow, real-time calibration, too.
Yep, and all that information, the list of detected objects and their positions, the scan rate gets fed immediately into the attitude control system.
Which lets Gaia predict
Precisely where those detected stars will be when their light reaches the next set of CCDs further down the focal plane.
Ah, so the sky mappers act like scouts, telling the rest of the system what's coming and exactly when.
Perfect analogy. Scouts providing the target list and timing information.
And the diagram in the report makes this clear. You see SM1, SM2, then the next block is AF.
Astrometric field. That's where the super precise position measurements are made.
Then BP and RP.
Blue photometer and red photometer. They have prisms that spread the starlight out into low-resolution spectra. Basically, measuring star colors very accurately, which tells us about temperature and composition.
And RVS?
Radial velocity spectrometer. For brighter stars, this takes much higher resolution spectra to measure how fast the star is moving towards or away from us, its radial velocity. Crucial for understanding galaxy dynamics.
So much science packed onto one focal plane. And there are other bits too. WFS, bam.
Right. Wavefront sensors to check and maintain telescope focus, and the basic angle monitor, which uses CCDs to constantly measure that critical 106.5-degree angle between the two telescopes.
Okay, so the sky mappers find the targets, predict their paths. Then for the AF, BP, RP, RVS, CCDs, this is where the windowing happens.
Exactly. Now that Gaia knows where to expect a star, it doesn't need to read out all the pixels on these subsequent CCDs.
Just the small patches.
Just small windows centered on the predicted arrival position and time of the star image. This is the huge data reduction step.
How small are these windows typically?
The report gives the numbers. Across the scan direction, it's usually 12 pixels wide. That's about 2.1 arcseconds on the sky.
Tiny.
Tiny. And along the scan direction, it depends on brightness. 18 pixels long for medium bright stars, only 12 pixels long for fainter ones. That's about 1.1 or zero point 0.7 arcseconds, respectively.
So you're only grabbing the light from the star itself and a tiny bit of surrounding sky.
Pretty much. Just enough to capture the star's image profile accurately.
And you mentioned binning for faint stars.
Yeah, for stars fainter than about 13th magnitude, the report says they bin pixels together in the across-scan direction before reading them out.
Combining signals from adjacent pixels.
Right. It reduces the impact of readout noise, letting you measure fainter things more accurately. It sacrifices a little bit of resolution in that direction, but it's a worthwhile trade-off.
Smart. And I guess there are rules for crowded areas. Or stars really close together?
Yes, the system has logic to handle dense fields and closed binary stars, allocating windows appropriately to avoid overlap or confusion as much as possible.
And does the slight sideways drift of the image cause problems? Smearing.
There is a small transverse motion, but the report notes that the TDI process and the across-scan binning help minimize any significant blurring from that.
Okay, now one detail from the report caught my eye. The shape of the pixels themselves. They're not square.
That's right, they're rectangular, elongated. The report says a 3-to-1 aspect ratio, 10 microns by 30 microns physically on the chip.
Why make them rectangular?
It's actually driven by the shape of the telescope mirrors. They're also rectangular, 1.45 by 0.5 meters.
Ah, okay. And a rectangular mirror creates a slightly stretched image.
It creates what's called an asymmetric point spread function, or PSF. The star image on the detector isn't perfectly round. The pixels are shaped to better match that PSF.
So the pixel shape is optimized for the telescope optics.
Exactly. And the report notes that the resulting image width in the scan direction is very narrow, around 0.1 arcseconds. That's what really sets Gaia's ultimate sharpness or resolution.
Even though the pixels are longer in the other direction. And these CCDs are packed, right? How many pixels per chip?
4,500 pixels along the scan direction
Wow.
and 1966 pixels across scan. Millions of pixels per chip and 106 chips.
But here's the cool part. The report mentions that even though each individual observation is kind of like a one rescan because of the TDI,
Right. You're mostly getting information along the scan direction at any instant.
because Gaia observes each star about 70 times over its 5-year mission and from lots of different angles as the spacecraft rotates.
The scan direction across a star changes each time.
You can combine all those different 1D scans back on Earth to reconstruct a full 2-dimensional image of the star and its immediate surroundings.
It's pretty amazing image reconstruction, yeah.
Yeah,
Turning these multiple slices into a 2D picture.
that really is clever.
It truly is. And yeah, listeners want to go even deeper into the onboard detection, the windowing logic. The report points to some key papers by Fabricius and colleagues and Oranu and colleagues published later when the mission was flying.
Good pointers for further reading. Okay, so let's try and wrap this up. This deep dive into Gaia's early design report has really shown, I think, what an incredible piece of engineering this mission is.
Absolutely. That onboard detection system, it wasn't just a nice to have. It was born out of sheer necessity. How do you handle that data flood?
Right. Manage the overwhelm while still getting the absolute best science. It's remarkable.
And what stands out is how that constraint, the data volume, actually forced these really creative solutions, like the time-delayed integration, the sky mappers. It let Gaia become its own real-time surveyor.
Yeah, moving beyond static catalogs, enabling discoveries of things that change or move. For me, the real aha moment is grasping that the decision to process on board To be intelligent at the source about what data matters wasn't just practical. It was fundamental to making Gaia feasible and enabling its revolutionary science.
Couldn't agree more. It fundamentally changed the mission's capability.
So here's a final thought for our listeners to chew on. Think about these principles: onboard processing, intelligent data selection, developed for something as, frankly, out there as Gaia.
Hmm.
How might these same ideas apply to other huge data challenges right here on Earth? Where else are we drowning in data, and could smart localized analysis be the key?
Yeah, what other seemingly insurmountable data problems could be tackled by analyzing information closer to the source instead of just trying to ship everything somewhere else?
Definitely something to think about.